All right, this is section 15.3, Thermochemical Equations. The objectives here are to write thermochemical equations for chemical reactions and other processes, and describe how energy is lost or gained during changes of state, calculate the heat absorbed or released in a chemical reaction, and we're going to do a combustion reaction is anything that reacts when a substance reacts with oxygen, releasing energy in the form of heat and light. Okay, so we're going to talk about those in this section also. We're going to talk about this is our vocab here, thermochemical equations, enthalpy, the heat of combustion, molar enthalpy, heat of vaporization, molar enthalpy, and heat of fusion. So we just mostly call these heat of vaporization, heat of fusion. The main idea is that thermochemical equations express the amount of heat released or absorbed by chemical reactions. Okay, so a thermochemical equation is a balanced chemical equation that includes all the physical states and all the reactants and products and energy changes. So it's everything we've been doing, but it also includes the energy change. So that's the difference between what we've been doing and what we're going to do now. The enthalpy heat of combustion of a substance is the enthalpy change for a complete burning of 1 mole of the substance. Okay, so here's some standard enthalpies for different compounds: sugar, octane, glucose, propane, methane, how much heat how many kilojoules of heat they release when you burn 1 mole of that substance. Changes of state. Molar enthalpy, heat of vaporization, refers to heat required to vaporize 1 mole of a liquid. So it can also go the other way. So they defined it here as to change something from a liquid to a vapor, but it's also the heat that a vapor gives up when it goes back to being a liquid. So it's just that, that process of becoming a liquid or liquid turning into vapor, that required heat, vapor going back to liquid that gave up heat, but we'd use that same value to calculate that heat that was given up or the heat that was needed to cause that change of state. Same thing happens when we melt something. If we melt it, we added heat to it. If we freeze it, go from liquid to solid, then that's the same amount of energy is required in reverse, right? We had to take away that amount of energy, or we had to add the amount of energy, depending on whether we're melting or freezing. Okay. So the change of state, standard. We've used these a couple times on the worksheets we've already had. Water is we use water a lot, right? Water is 6. That's the heat of fusion. The heat of vaporization. That's how much kilojoules it takes to freeze or melt a mole of water. And this is how many kilojoules it takes to heat up or condense, to vaporize or condense a mole of water. Okay, phase changes for water. Start out with solid water. We need to add 6 kilojoules of energy to melt the water. So that's the heat of fusion. Okay, so if we're going from solid to liquid, we're adding that. If we're going from liquid to solid, we're taking that much heat away. Same thing here. We're going from liquid to gas, we're adding 47 kilojoules. If we're going from gas to liquid, we're taking away 40.7 kilojoules. Combustion reaction is the reaction of a fuel with oxygen. That's what happens in our cars all the time. That's why it's called an internal combustion engine. In our bodies, same thing happens. We breathe oxygen, right? And at some cellular level, there's some combustion going on where oxygen is used to create energy and heat. And creates chemical energy, and heat is a byproduct of that we use to keep our bodies at the right temperature. Okay, so that's it here in brief on these substances. So answer the questions on the form below, and I'll see you guys in class tomorrow.